Hi there. My name is Yuri Kolonin, and I study at the Novosibirsk State University. Today I'd be talking about what is task-based approach to AI modeling. According to the theory of functional systems, that is the biological theory. Also, I'd like to present the mathematic modeling that was specifically developed for this approach. And also we'll show you a few cases, of course. As you probably are aware, there is no unanimous opinion about what sort of technology stack should be used to create the so-called AGI. There are different opinions about that. Neural networks are, of course, becoming more and more popular, but the question is what will be used to create artificial general intelligence. Of course, neural networks are good at certain tasks, but they are limited in many ways. For example, high computation costs, large volumes of data that we need to actually train every single neural network, and of course the infamous black box problem, which means that we can see the result of the computing, but we don't know how they were actually output. We cannot look inside. All of these things raise questions about the future of AGI created on the basis of neural networks. Another approach that was specifically popular in the aughts is cognitive architecture. Cognitive architecture is the attempt to model certain functions of mind or brain based on certain biological theory. It can be pure engineering as well. Purely hands-on. What we suggest is actually cognitive architecture. It has been developed in a task-based paradigm based on the theory of functional systems. This is the neurophysical, this is a theory of neurophysics that was initially developed in the USSR, specifically to study task-oriented behavior. The key postulates of the theory is that we can talk about any goal if there only if there is the criteria for having that goal achieved. According to TFS theory of functional systems, the organism, while reaching the goal, creates certain hierarchical plan to achieve that goal. So, envisioning the achievement based on the experience. In the same time, the organism builds the hierarchical mechanism that includes criteria for the achievement of the task and subtasks. So the formalization that we suggest is a type of cognitive architecture based on rules. And it has been created with the logics of logical probabilistic learning. The logics here is meant to reveal the very specific, the most specific rules that determine the behavior of the agent. This theory does not only model real-life cognitive processes. This model actually is very efficient according to the experimental results that we have been getting. This sort of formalization can not only cope with the tasks that are already being solved with other methods like reinforcement learning, not only solves that tasks more efficiently, it can also handle the tasks that are not solvable with more traditional approaches, and I will talk about that in more detail when I get to experiments. And our model also can be categorized as explainable. So that means that we can look under the hood and actually look and see how the computation was made. So, again, theory of functional systems, TFS, is the theory of neurophysics that has been developed in the USSR by the disciple of Mr. Pavlov. It was developed by Mr. Anokhin. You probably know his grandson, Konstantin Anokhin. He is a well-known person who is an advocate for neurobiology in Russia. According to the TFS, the key notions are desire, a goal, and task-oriented behavior. Task and task-oriented behavior. Desire is always active. It is some sort of active phenomenon. Since it's pointless to wish something if there is no any way to do anything to implement the desire. All of the actions are, of course, purposeful. So if there is no purpose, it goes without saying that you don't know what should be done, and that there is no criteria. You can, and there must be a criteria, because without a criteria, you can just claim that the task has been executed, the purpose has been achieved right away. The knowledge about the purpose, however, does not contain the information how, when, and where this, and with which tools this goal can be achieved. I mean, we cannot set a goal, we cannot have a purpose if we do not have criteria for achievements and we don't have tools to achieve that. That's called the paradox of solving goal. Our brain is constantly busy with solving this goal paradox. This is something that multifunctional systems do. Multifunctional systems are constantly solving the goal paradoxes. The central mechanisms in this approach are afferent syntheses for decision making, and also acceptor of action results. Afferent synthesis is naturally the goal setting. It consists of motivational excitement. That is the signal to the organism that the body has certain needs. When the organism gets the signal, it extracts from the memory all of the known ways to kind of cover this need, to fulfill this need, and then the organism selects the ways to achieve these goals that are available at the moment. So we can have situational and triggering afferentation. After that, the organism makes a decision about a certain single way to achieve the goal at a given moment of time. And the organism selects the way that, according to experience, has the highest potential, meaning the way that was mostly successful in the past. In the same time, the body builds the set of acceptors of action results, which is the hierarchy that I mentioned. It contains the criteria to achieve the goal and criteria to achieve all of the sub-goals and sub-tasks. Therefore, after the cycle is concluded, our initial paradox goal becomes the actual goal for which there is an awareness of how, with what, and when it is possible to achieve that goal. Now, let's look at the math formalization. Let's look at the certain engine which operates in discrete time. It has a set of sensors. And for every sensor, we have the set of possible observations. So if it's an optical sensor, for example, we can observe green light, blue light, no light, etc. Also, the engine has lots of known actions: go forwards, go backwards, jump, duck, etc. The state of the system, the state of agents at any given point of time, can be coded as data from every sensor available. And the set of all the possible states can be assigned with predicate. We can set predicates for the set of possible states. For example, sensor informs the agent that it's super hot, there's sand, there's sun. Then we get the predicate that, for example, the agent is in the desert. So, transferring it from the language of sensor, we can recode the state of system into the language of predicates. So the agent simply looks into the list of all known predicates, checking which one is true at the given point of time. We can also highlight target predicate, which is structurally the same as all the rest, but the agent specifically knows that this is the default state. For example, default predicate, find human. or kill human. Anyway, this cognitive architecture is based on rules. We need to explain what a rule is. That is the set of 4 that contains the initial state, the default state, the action, and the probability of success, which is P. Translating that into Russian language, that means that action A will transfer the agent from state S0 to SE with the probability that equals P. So, the agent contemplates the following way. If I follow the voice, I transfer from the state hear voice to the state found human with a probability of 90%. The probability is very quickly and easily to find. That is the amount of successful cases divided by the general number of the cases when the rule was applied. That's pretty clear. Now let's give a definition of this most simple functional system. That is the set of n plus 2 that also contains probability, also contains the target state, and the n number of rules that I have described, of the type that I have just described. This is how this looks. You can see here the words that are more familiar to you, and this is logics of the functional system. It completely duplicates the logics that I have described when I was saying about how it works in the human mind. So again, we have 2 states entering into the agent, and the agent knows about its current state and its target state. The efferent synthesis is being launched, and it extracts all the rules that can be applied in the situation and would lead to the desired result. After that, the decision is being made about which of the rules will be applied based on the principle of highest probability, again, based on experience. So the rule is selected, the rule that is selected helped most of the times in the past. Then the probability of success is being calculated. The agent makes an action according to the rule, and as a result, the acceptor of action results actually compares the result to the expected result. If the result corresponds to expectation, then the rule gets the probability premium. So therefore, in the future, the rule will be used more often. If the action did not lead to the intended result, then the rule gets penalized in terms of probability. And of course, the probability for that rule becomes lower. Let's tell about what's a more complex functional system. This is naturally a recursive definition. Again, this is the set of n plus 2, but we have actually functional systems within it, not the rules, not only the rules. So in the end, we get a hierarchy tree, where's the functional system with the high tier that leads to a certain goal, and it has subsystems, functional subsystems, which can get the control. And all of the computation is happening the way I described it. And we're talking about ranked set here. So this set can be able to identify sub-goals. It can build subsystems, subsets. I will not have enough time, unfortunately, to go into detail about that. But let me describe our experiments. That's what matters. The first experiment was very simple. Looking for food in a rectangle-based field. We have this field, which is split into rectangles. It's pretty big. And there is a certain defined default number of food. If the food is being eaten in one cell, it appears in a different cell. And the number of meals in this field is constant. We have the agent, which has 3 things to do. Turn left, right, make a step forward and backward, and it has 9 sensors that are in charge of the cells around, and around. The task is that the agent should find the largest number of food, the highest number of food in a given period of time. We compared our system, the agent, based on the TFS, with other approaches from reinforcement learning, such as Q-neural network and Q-table. Here is the result of the experiment. As you might see, Q neural net, which is the red line on a graph, achieves the results comparable to semantic inference by the end of the period of the experiment. But you see that the system needs much more time because our engine gets to the peak much, much quicker. The other experiment is a more complex version of a previous one. There's also food and the rectangle field of cells, but in addition to food, there are also pills. So the food is red, the pills are blue. The idea here is that it is impossible to eat food without first getting a pill. So the agent must first eat a pill, then a food, then a pill, then a food. If the agent eats food before a pill, that does not count as the food being eaten. In this experiment, the agent has 10 sensors, 9 just those that we had previously, and one more sensor also defines whether the pill has been eaten or not. The experiment is naturally the same. And we try to compare this approach with other traditional models as well. You see the graphs. Both approaches that we compare to show starkly different results. We are far ahead by the factor of 3. Additional experiments, however, showed that Q neural net can improve its results, but it needs huge figures such as 3 to 500,000 steps. So the experiments show that the architecture is quite promising. I mean, there are different things that we could try here. We have actually executed a few of those, but I cannot show all of them on the slides, but I'd be glad to tell you in the Q&A session, or you can just get in touch with me. And we have this website, Scientific Discovery. We have published lots of data about this subject. And also you can write me directly on email or ask right away now on the chat. Thank you for your attention. Yuri, thank you. A few questions. Let me just ask them right now. Will there be ever a way to assign AI with some sort of consciousness? And what is missing now? Well, that is a broad question, because this sort of task, as I have said, I mean, the goal only means if we have the criteria to achieve it. So we need to understand what is consciousness for the machine. We need the criteria. We don't have it. The construct of consciousness is a bit vague. It's a generalization of different brain functions. So I would believe that we need to set the goals more clearly so that the machine would be able to kind of make an impression of being conscious. Let's put it that way. Let's call it conscious. Okay, accepted. Yet, is it possible, will the AGI be created as the replication of human brain, or there is a completely different way? At the moment, we are researching AGI based on kind of a mimicking human brain. We are now using biological theories at the moment. This is the approach that we selected because it has worked at least once already for the kind of a natural development of things, but there might be developments without any similarities in the natural world. But we are now following the natural way, and it seems to be working. However, can we model consciousness? What is consciousness?